Okay. Okay, good morning. Surprisingly, we got quite a full house today. Like, I almost thought I was in the wrong room. But okay, welcome back and welcome to the very last lecture of your second year econometrics course. So likely the last time I'm seeing you guys before autumn, I guess. So the plan for this lecture is that I'll go through the mock exam paper, which I think we should be able to cover it within this particular one. So I'm not going to use the lecture in the afternoon, but I'll be in my office. So if you have questions, you're more than welcome to pop by and ask. Now, I just sent out an email announcement this morning. Not sure whether you have time to check it. But basically, you can find the office hours for next week. So pretty much we have ATA covering one day next week. Office hour will be on Friday morning, just before the exam. Okay, so whichever slot that fits you, you can just pop in, either join online or some of them are in person. These are in the semester 2 timetable page, or you can just check the announcement I sent this morning. And those of you who have not done quiz 4 yet, make sure you've done it before 5 p.m. today. Okay, so I guess this is what you're more interested in, the mock exam paper. So this session A essentially is related to what we've been discussing in the past couple of weeks post-Easter. Now, what we have is, so we have a study that is designed to explore the impact of kindergarten class size on your wage at age 40. And we're told that the participants are randomly assigned to either small or regular classes during their kindergarten years. Then basically, assuming we have correctly implemented the RCT, then we shouldn't be worried about, selection bias. And basically, we also have no selectional returns because randomization basically ensures the treatment and the control groups have identical characteristics on average. So every single person is likely to appear in the treatment or the control group, making the mean potential outcomes, regardless of being treated or not, to be the same across both groups. So this is something you have to keep in mind. That's basically the advantage of a correctly implemented RCT. And in this study, basically we have 3 variables. The first one is our treatment variable, which is the D, class size assignment, and our outcome variable of interest, earnings at age 40. And there's also an additional variable X, which is the total years of education by age 40. And immediately, by just looking at this X, we know that it cannot be a pre-treatment random variable. It's a post-treatment variable, and it is likely affected by the kindergarten education, which means this is a post-treatment outcome, an interim outcome that's likely affected by D. Then in any case, given what we've discussed in the past couple of weeks, we know that including interim outcomes in our analysis will reintroduce selection bias, even if selection bias was originally eliminated by RCT. So interim outcomes are bad controls. One should never include post-treatment outcome variables in causal analysis in order to consistently estimate the causal effect of interest. Okay, so here, what we have is that we're given a population linear regression model, and you're asked to explain what this beta 1 represents in this context, focusing on its descriptive interpretations. Then, given we have a dummy variable, the D is a dummy, we know that basically that just represents an intercept change. Essentially, we have different average values. When D is 0, let's say when D is 0, then we'll have the conditional expectation of Y given that D is 0 is just equal to the beta naught. So basically, beta naught gives the average or the mean observed outcome for the control group. And when D is 1, we'll then have the conditional expectation of Y given D being 1 is equal to beta naught plus beta 1. So the sum of the two betas will give us the mean observed outcome for the treatment group. Okay, remember the Y without the superscript is the observed outcome, the actual outcome that we observe in reality. So the actual outcome that we observe for those D being 0 is the same as their potential outcome in the untreated state, whereas for those D being 1, so in the treatment group, we only observe their outcome for the corresponding treated state. That means the Y1 for those in the control group remains the counterfactual, and likewise the Y0 for those in the treatment group remains the counterfactual. Then given this, essentially beta 1 just represents the difference between the two observed mean outcomes between groups. That's it. That's all you need to discuss for a descriptive implication. You don't need to infer anything about causality yet. That's related to part B. So part B then asks what causal interpretation can we be given to the estimated beta 1, and would the exclusion of, family background or other individual characteristics in the model raise concerns about omitted variable bias? Given what we just discussed, no, right? Assuming correctly randomized the treatment and the control group assignment, then we shouldn't be worried about omitted variable bias because randomization ensures that the potential outcomes, so the Y1 and the Y0, this is independent of the treatment assignment. Okay, then given this independence, there's no selection bias, no selection on return, then using the fundamental equation for causal inference, if you recall what that is, on the left-hand side, we have the observed difference between groups, okay, which is essentially the difference that we compute in part A, the yi1, which is the observed outcome for those in the treatment group, subtracting that, the mean observed outcome for those in the control group. And this is equal to the ATT plus selection bias, where the ATT is essentially the treatment effect for the treatment group. So we look at the Y1i minus Y0i conditioning on being in the treatment group. And the selection bias is basically the comparison between the treatment and the control group in the untreated state. So this is the same as the untreated state outcome for the treatment group minus the untreated state outcome for the control group. Then, given independence, the potential outcomes are independent of the treatment assignment. This ensures conditional mean independence. So these two conditional expectations are the same as the unconditional one. Therefore, there's no selection bias because subtracting one term by itself is just 0. So essentially, there is no selection bias in this case, then the observed difference between groups using the fundamental equation of causal inference gives us the ATT. And on top of that, there's no selection on return because, again, using the fact that the potential outcomes are independent of the treatment assignment, this conditional expectation is the same as the unconditional one, which is essentially the ATE. Okay, so no selection bias, and similarly, no selection on returns. Remember, selection on returns occurs when the ATT differs from ATC, and given that the average treatment effect for the treated is different from the average treatment effect for the control, the overall average treatment effect in the population must be different from both. So, given we've established these identities, then the beta hat 1, which consistently estimates the beta 1, it also consistently estimates the ATE and the ATT. So we can interpret the beta hat 1 as the estimated average treatment effect on the treated or the estimated average treatment effect in the population. And there's no concern about omitted variable bias. So that's for the part B. Now, the very final part of this question relates to the X, the interim outcome. And we've already discussed we should not include interim outcomes in our causal analysis because that would reintroduce the selection bias that we wanted to avoid. If we look at this regression model where we included X and the corresponding causal model, then we have the, let's say, phi naught plus phi 1 di plus phi 2 xi plus epsilon I. Now, nothing wrong with this as a causal model, but it's just that this formulation of the causal model will not allow us to consistently estimate the causal effect that we're interested in, okay? So it does not allow us to consistently estimate the phi 1, but if in the end of the day we don't care about estimation, we just want to discuss some causal story, then this causal model is fine as it is, okay? So first of all, given that we have random assignment, assuming that that is correctly implemented, we know that DI must be independent of all other pre-treatment characteristics that affects your wage at age 40. And these other characteristics that affects your wage has not been directly included in the model. Therefore, they are in the causal model error term, epsilon, and they're independent of D. However, X is your education at age 40. Y is your wage at age 40. Epsilon could likely include innate ability. While random assignment ensures these kind of unobserved characteristic innate ability to be independent of the treatment variable D, innate ability likely affects one's education attainment at age 40. So they are correlated. And likewise, innate ability must affect one's wage. You know, how able you are obviously would determine or influence how much you can earn. So innate ability definitely belongs to the epsilon. Then we have an issue here. The X, the interim outcome, is endogenous. And at the same time, this interim outcome is affected by D, the treatment. Your kindergarten education is likely affecting your education attainment at age 40. So the covariance between D and X is also different from 0. So while D itself is exogenous, the endogenous X being correlated with this exogenous variable D renders OLS inconsistent for all the causal model coefficients. So no consistent estimate of the causal effect in this case. Therefore, we can't consider the lambda hat 1 as consistently estimating the causal effect of kindergarten class size on earnings at age 40. Okay, so that's basically all you need to discuss for this part A question. Should be quite straightforward. Okay, so if you're happy, then I'll move on to part B. Okay, now part B comes back to where we were, sorry, where we were before the Easter break. So in part B, we have an ADL model of order PQ. So remember, the first letter, the P, always stands for the AR order, and the second letter, the Q, always stands for the DL order. So DL is the distributed lag. So basically, the number of lags coming from a different series. So here we have an ADL model for log consumption C, and the Y here represents the log income. And we have a sample from T, well, effective sample from T equals to 1 to capital T. And what we assume here is that the error term is an IID white noise with mean 0 and a constant variance, and that this is independent of all past information up to time t minus 1. So the future shocks are independent of past information contained by the consumption and income. So this is a very important assumption that we will need to use in later parts of this question. Now, the first part A, asks us to discuss the motivation for using this model and specifically why we should include the log income as a predictor for the log consumption. I mean, obviously, income is correlated with one's consumption behavior, and how much you earn will determine how much you can spend. And it's not just how much you earn at the current period that matter, but also how much you earn before also matter. So that makes sense to include lags of Y in the model to predict your future consumption behavior. And we also asked the question why we omitted the delta YT in this model. Okay, we see that in this model equation, on the left-hand side, we have the delta CT, which is the first difference of the contemporaneous consumption. So essentially, this is CT minus 1. And we included the first 4 lags of the delta CT. So here we have delta CT minus 1 all the way to delta CT minus 4. P, I mean. And similarly, we have included Q lags of the first difference, delta YT. So we have delta YT minus 1 when J is 1, and all the way to delta YT minus Q. Obviously, we didn't include delta YT on the right-hand side. Why? If we go back and read the first sentence, this is a forecasting model. We want to forecast the future. The delta YT obviously happens at the same time as delta CT. That is in the future. We can only use past to forecast future, but not use future to forecast the future itself. Therefore, the delta CT is excluded because the delta YT is excluded because it's in the same time period as delta CT. So this is a future or the same time period as the delta CT, and we need past information to forecast future values. Okay, so basically this is just a logical question. Why should we include or not include something just because we want to predict the future? Okay, yes?
Sorry, can we also say that because you know how it says UT is independent of all past information, YT and CT, we could say that UT, it doesn't say that UT is independent of the current YT.
You mean UT is independent of?
Yeah, it's in the question says that UT is independent of past YTs, but it doesn't say that UT is independent of current YT.
Well, this assumption is on the basis that we have only included lags. Had we included the delta YT, then obviously we can change the assumption to that the UT is independent of all past information of Y up to the current time period. But sometimes we can also just keep this assumption, and basically that is also something that's logical, right? The shock at the current time period is likely affecting both income and consumption. So the sort of reasoning here doesn't really go from the error term, but goes from the purpose of the analysis, okay? So that's the part A, okay? Make sure you read the given statements or informations in the questions carefully. So that's the first part. Now, the second part. Basically, you should by now be very, very familiar with this type of table, which contains the statistics from the ADL test, okay? And we've been seeing this over and over again in a lecture, in the quizzes, and in a homework problem set. So if you don't know how to find the correct specification, or if you don't know how to reach the conclusion as to whether there is a stochastic trend or not, make sure you go back and revise the notes. So in part B, we're given the ADL test results. And the question asked, based on the results given, why does the model in 1 uses the variables in first difference rather than the level? And you're asked to discuss the findings at the 5% using the general to specific approach. Essentially, this question wants us to pin down the order of integration. Okay, so you're given all the statistical tables as the appendix in the exam paper. So we start from the most general specification, the constant and trend. And given that we're interested in a 5% test, so we should compare the given test statistic to the critical value of minus 3.43. And obviously we can see that both of the given test statistics are not more negative than the critical value, so we fail to reject the null. Okay, the null is that the pi is 0, which corresponds to that there is a stochastic trend in the M, where this M is the level, either the level of the log consumption or the level of the log income. Then, given we fail to reject the null, we should move on to the next step, test whether we should indeed include a trend in the test. Then now we move on to look at the F statistic critical values, and we should look at the phi 3. And given the 5% test, the critical value is 6.49. Now, the null hypothesis is that the pi and the delta is a coefficient on the time trend, being jointly insignificant. And we will only reject the null if the test statistics were greater than the F statistic. But obviously here, both are smaller than the F. So again, we fail to reject the null, which suggests that the trend should be dropped. Okay, and given that we should remove the trend, then we need to move on and look at the constant-only test. So now we need to use a different critical value because whether we include more deterministic trend or not, that affects the distribution of our ADL test statistic. And now that we can see that the critical value becomes less negative compared to the critical value associated with a trend-inclusive test. Originally, it was minus 3.43, but now it becomes minus 2.88. Remember, the more deterministic trend you include, the more the distribution will shift towards the left. So once you remove one trend, it will shift back towards the right, becomes less negative. So again, we want to compare the test statistic with the minus 2.88. And clearly, these are less negative, so they're greater than the minus 2.88. So we will again fail to reject the null. Okay, so we fail to reject the null that there is a stochastic trend, and we need to then move on and test whether we should keep the constant or we should remove the constant from the test specification. So we need to then check the F statistic table in the appendix. So we need to look at the phi 1 value that corresponds to 5% test, which is 4.63. And now we can see that both of the F statistic for the tests in the income and consumption, they are greater than the critical value. So this would lead to the rejection of the null hypothesis, which suggests that the constant-only test specification is the most appropriate one. Okay, and given that we have failed to reject the null in the t-test, so that implies both the y and the c, so the income and the consumption, they have at least one stochastic trend. So each has at least one stochastic trend, but we don't know whether they have exactly one or they have more than one. To pin down the exact number of stochastic trend, we then need to move on to test for their first differences. So we then look at the columns associated with the delta C and the delta Y. And given that we have decided the constant-only specification to be the most accurate specification for the level, then we should start from the constant-only for the first differences as well. So we first look at these two values. And again, we will compare them with the minus 2.88. And obviously, both are more negative than the minus 2.88. Then this implies that we would reject the null, which suggests that delta YT and the delta CT does not have, well, they do not have a stochastic trend or a unit root. So both the delta YT and the delta CT are integrated of order 0. And given we have found that Y and C have at least one stochastic trend, and combining with the fact that their first differences have no stochastic trend, then we can say something about the exact order of integration for Y and C, that they are both integrated of order 1. They both have exactly one stochastic trend. So Y and C, they are not stationary, given that they contain stochastic trend. And remember, the purpose of this question is to conduct forecasting. We're interested in forecasting. And remember what we have discussed in the topic of forecasting, that we prefer to use stationary variables to run forecasting because that ensures we have bounded forecasting error. Okay? And on top of that, when it comes to testing for the unit root, we also mentioned one drawback of having a unit root process is that the ORS estimate tends to bias downward, okay? Which is why we prefer to use the burst differences. The burst differences are the stationary transformation of the original non-stationary series. By transforming to a stationary series, we have more stable statistical properties and we have bounded forecasting error, and that will give us more accurate prediction using the first differences rather than using the original levels. So that's basically all you need to answer here for part B, identifying the exact order of integration, and that it's the first difference that is stationary, not the original one. And we prefer using stationary variables for forecasting. Good? Okay, so let's move on to part C. Now, part C is a rather simple part. So this ties back to when we talked about selecting the optimal AR order. So here we have that the maximum possible value for P, so the maximum AR order available is 8. And the question asks, why not direct? Is it? No. Okay. So why not include all A lags of the delta CT? Then, given what we have discussed when we were talking about selecting the optimal AR order, so while it's beneficial to have a large P in the sense that the model will be more flexible, and that also reduces bias in the case where the series does have a long history, but a risk of having a large estimation variance because we have more parameters to estimate. That definitely increases the standard error associated with our estimation. On top of that, we risk overfitting. So including too many lags might make us fit the in-sample data too well, but that is sort of compensated by having a worse out-of-sample prediction. Okay, because sometimes when you use too long an AR lag, then you're not only capturing the true sort of pattern in a series, but also you're capturing the noises. These noises tell us nothing useful about the true underlying pattern. Therefore, when you attempt to use an AR model with large number of lags to predict out-of-sample data, your prediction performance will tend to be worse compared to selecting a relatively moderate order for the AR lags. Okay, so we should not include all A lags, and detailed and appropriate methodology, either use the IC or use the stepwise downs testing by the t-test. These are all in the notes. I'm not going to go through them in detail. If you're not familiar with information criteria or a stepwise downs t-test, make sure you check the lecture notes. Okay, so that's for this part C. Now, the next part, part D. What's wrong with this? Okay, cool. So the part D is related to the last lecture in time series. So in this question, we're asked whether the change in income greater caused the change in consumption at the 5% significance level. So essentially, this question asks us to test whether we have Granger causality. We want to test for Granger causality formally. Now, one thing you have to keep in mind, while there's a term causality in Granger causality, it's not the causality that we're discussing in topic 5. It's Granger called this causality, but actually it's all about prediction. It's about predictability. So a more accurate term is whether the change in income helps to predict the change in consumption. Okay, so we were told that we can set both the P and Q at 4. So essentially we have an ADL44 model. Where we have the 4 legs of the consumption and also we have 4 legs of the delta YT. Then to test whether the change in income Granger causes the change in the consumption. Basically, we're testing whether these 4 lags of income helps to predict the future change in consumption. Essentially, we're testing whether all these betas are simultaneously 0. So under this null hypothesis, the delta YT does not Granger cause the delta CT. Okay, because the delta YTs do not carry useful or extra information apart from the delta CT's own lags that is useful for predicting the future change in consumption. And the alternative hypothesis here is just that at least one of the betas, let's say the beta K's, is different from 0. For the K in 1, 2, 3, 4. Okay. Then in this case, under the alternative, we'll have that the past or the delta YT does Granger cause delta CT. So the income does carry extra useful information for predicting future consumption. So this is the Granger causality hypothesis. And one thing you should keep in mind, whenever it comes to specifying hypotheses, the hypotheses are always about some population coefficients, some population moments. They are never about the variables themselves directly. Okay, this is about the beta 1 to the beta 4 being 0. It's not that the delta YT minus 1 equal to delta YT minus 2 all the way to delta YT minus 4 being 0. It's the coefficient. This is a common mistake that a lot of people made in the semester 1 final exam. Okay. In the F-test construction, a lot of you, instead of formulating the hypothesis in terms of the model coefficient, you formulated a hypothesis in terms of the X, and this is not correct. Okay, hypothesis testing is about the parameters, the population moments, the expectation, the variance, but not the variables themselves directly. So be careful with the way that you formulate the hypothesis. Then, under the null hypothesis, essentially, the restricted model is the AR4 for delta CT. Okay, whereas under the the alternate hypothesis, the unrestricted model is the original ADL44. Then to test the joint hypothesis, which is essentially testing that we need to exclude all 4 lags of the delta YT. So the relevant F statistic is the one given in the last row, the 1.0958. And this F statistic should be compared against the critical value at the 5%. So we need to look for the usual F table. And here we're interested in testing 4 hypotheses. We're testing for 4 restrictions, beta 1 all the way to beta 4 being 0. So the critical value here is the 2.37. And we can see that the F statistic is smaller than the critical value. So we would fail to reject the null. Which suggests that the delta YT does not Granger cause the delta CT. So when you interpret the conclusion of your hypothesis test, make sure you interpret it within the given context of the question. Okay, so that's how you test for Granger causality. Basically, it's about predictability. So that's all related to the part D. Yes? Sorry, I can't really hear you. Why don't we use the second one?
Because that's kind of what we explained from the very beginning.
Should we exclude all the regressors?
No, the second one.
You mean this one?
Yeah.
Why should we exclude lags of the delta CT? The model, the dependent variable, the delta CT is the variable that we're interested in. And Granger causality is about testing whether variables or information coming from a different series help to predict the given series. So it's about the YT coming from a different series help to predict the C, not about whether the path of C itself helps to predict the future value of C. Make sure you go back and check the final lectures, the final set of lecture slides on Heim series, okay? It's not F statistic for excluding all lags of delta CT, but it should be the one that we exclude all lags of the delta YT, okay? So that's the part B. All good? We're nearly there. Only 2 more parts left. And obviously, we'll be able to make it finish on time. So, part E. What is the minimum MSFE forecast? That is basically the conditional expectation, right? So, suppose we are interested in forecasting let's say, 1 step ahead. Then, given information about consumption, let's use this curve. So all information about consumption and income, then the minimum MSFE forecast is the best functional form of the given information that best predicts the CT plus 1 in a sense of giving the smallest prediction error. And we know that the solution to the best general prediction problem is essentially the conditional expectation. Okay, so this is the minimum MSFE forecast. And the question asks, how can we obtain a feasible 1 step ahead forecast for the level of consumption? So here we're interested in forecasting the CT plus 1, not the delta CT plus 1. Okay, now the model given in the question is actually the ADL model for the delta CT, but it does obviously contain the information for the CT plus 1. So the CT plus 1, which is the 1 step ahead, or like the future for the level of C, is equal to the change, which is the CT plus 1 minus CT plus the CT. That gives us the future value. Now, this is our plus the capital. This is our delta CT plus 1, which can be predicted or forecast using the given model. CT is the last observation in our sample. This is given. So knowing the forecast value for the change and given the data set, obviously we can recover the forecast value for the CT plus 1, okay? So first of all, we know that the optimal forecast for the change in consumption, given all past information up to time t, is the conditional expectation of the delta CT plus 1 given CT and all the information for income up to time t. Then using a ADL44 model, okay, we have alpha naught plus alpha 1 delta CT plus 1 minus 1, which is just the delta CT, the change at the final time period, all the way back to the fourth lag, which is CT minus 3. And then we also have plus the beta 1 delta YT all the way back to beta 4 delta Y capital T minus 3 plus the U capital T plus 1. And this is given the information on income and the consumption. Then all these changes, essentially, they are already given in the past information. And similarly, all the changes in the income, they're given we know the history about Y, so they all become deterministic. We can just directly take them out of the conditional expectation. And the final term that is left is just the error term. But we were already told that the future shock is independent of past history. The U capital T plus 1 is in the future relative to the curly C and the curly Y. So they're conditional mean independence. Therefore, the expected value of the U, the shock at time capital T plus 1, given all past information, is 0. Therefore, the optimal one step ahead forecast for the change in consumption is just given by this expression. Then to compute the visible forecast, we just need to estimate the alphas and the betas using OLS. So estimate alpha and betas using OLS with the sample from t equals to 1 to capital T. Then we can just replace everything with a hat that gives us the visible one step ahead forecast for the change in consumption. Then this delta hat C T plus 1 given T, this is equal to C hat T plus 1 given T minus C T given T hat, which is essentially itself. And we don't even need a hat on top of the CT because this is known. Then to recover this, we simply take the difference between the computed one step ahead forecast with the final observation in our data set. Done. Okay, so the key is to construct the one step ahead forecast for the change in log consumption. then we'll be able to recover the one step ahead forecast for the level of the log consumption. And the question asks, considering your findings in Part D suggest a competing forecast model that could potentially achieve a smaller MSFE. So in Part D, we failed to reject the note of no Granger causality. Then essentially,